So random vibration oftentimes is used to simulate some sort of real world vibration scenario, whether it be transportation or machine operation, any of those real world vibration scenarios that we talked about a little bit at the beginning of this presentation. That's what you would use random vibration for. It's much more realistic than sinusoidal vibration, and that's because in the real world, the future of vibration is not predictable. So you need something much more random and sporadic to actually accurately simulate it. And you can see down at the bottom, I have put a figure of time domain data for random testing, and you can see it's very sporadic, especially when you compare it to a sine graph. Now for sine testing, the intensity is dictated by your G level or your actual acceleration. For random vibration, it's a little bit different, and the intensity is actually dictated by the GRMs. And that's essentially a measure of the cumulative energy input or a measure of how hard your shaker is really working. So to give you a better idea of what really is the GRMs, it's calculated just as the square root of the area under the profile curve. So you can see here, this is what a random vibration profile would look like on your actual shaker controller. And the square root of the area under that green curve, that's going to be your GRMs. Now, it is important to note also that while this GRMS does indicate your test intensity, two different curves with the same GRMS are not necessarily equivalent. They could have completely different shapes and different frequency ranges as well. So I want to talk a little bit about the X and Y axis for random as well. As I mentioned earlier, the X axis here is not going to be proportional to time. So rather than tracking along that green profile curve like we did with sine testing, with random vibration, at any point in time, your shaker could be operating at any point along that green curve. So it'll actually kind of bounce around that curve as you're performing testing. Also, I want to point out the y-axis. You can see for sine testing, it was just G's, it was just your acceleration. And in random vibration testing, we've got G squared per hertz. These units kind of confuse people sometimes, but essentially, when you take your acceleration, square it, and divide it by the frequency, you're essentially just normalizing those values. And this is important here because the acceleration during random vibration testing actually depends upon the bandwidth that you measure that acceleration at. So before you perform a test, the profile itself needs to be defined. And for random vibration, there's a few different ways of doing that, both graphically and by using a breakpoint table. And I've shown both examples here. You can see on the left, that would be an example of graphic representation of a random vibration profile. And it kind of speaks for itself. It gives a graphical representation of the actual shape of the curve itself. It gives you some key frequencies and accelerations. And then in this case, they actually gave you some slopes as well. And a breakpoint table, on the other hand, rather than giving you a graphical representation, it just gives you every single key frequency point and its corresponding G squared per hertz. And so when you look at vibration specifications and procedures, you'll see either a mixture of this or one or the other.